there's a little thing down at the bottom for slideshow. And all right, let's do it. All right. So this is the last set of speakers for this session, and let me introduce them with no further ado. So this is Ayan and Ayush, and I'll let them introduce their talk.
Alrighty, well, as he said, I'm Ayan. I go to Bellevue College Prep. That's Ayush. She goes to University of California, Berkeley. And our project is designing heat sinks for passive cooling of a high-power LED panel with applications in space agriculture. So let's start off with our problem. What are we trying to solve? Well, high-powered LED panels find a ton of applications, especially in indoor and space agriculture. However, unfortunately, these panels tend to generate a significant amount of heat, which deteriorates their performance, reduces their lifespan, and can even impact the overall system. In general, in order to cool these panels, both active and passive cooling thermal management techniques are employed, with active cooling techniques including fans and liquid circulation, while passive cooling techniques can include heat sinks, heat pipes, and thermosiphons. Unfortunately, many active cooling techniques have their own sets of problems, unexpected malfunctioning and power consumption being some of them. But also, they tend to add moving parts to the system. In comparison, passive cooling techniques do not need additional energy input and often can last significant periods of time without needing repairs. So that makes our objective clear. We're going to improve and work on a passive cooling technique by applying individual passive techniques, potentially combining them to make the thermal management system compliant. So let's start off with our LED panel. We have a 200 watt, 350 by 210 millimeter panel that when we first received it was being cooled by fans. And there were no passive cooling methods involved. So our final objective became to completely eliminate the need for these active cooling fans by using a combination of heat sinks, heat pipes, and thermosiphons. So we began our experiment. We removed our panel from its encasement and completely got rid of the fans. We then took the base temperature of just the panel itself without any cooling mechanisms. After that, we attached our heatsink to the panel and added thermocouples to the face of the thermocouples to the top and bottoms of 8 different fins using heat-resistant tape. After a 2-minute baseline, we turned the panel on and started to record our data with the heatsink on the panel. So our heatsink originally was composed of a basic standard aluminum heatsink, and we embedded 6 holes alongside the base of the heatsink to add our heat pipe system and our thermosiphon system.
So originally, when we were doing this, we were using just a standard off-the-shelf data logger. But we quickly found multiple problems with it, one of which being there was a lot of electrical interference. And we were getting ridiculous temperatures, like negative 20 degrees Celsius. So what we ended up doing was creating our own interlocking system. So using a Raspberry Pi, as you can see out there, we connected a 16-channel multiplexer to it, and we connected all 16 of our thermocouples to the multiplexer. And we ended up just using a Python program to automatically log the data and graph the data using the Raspberry Pi. And this not only fixed all of our interference problems, as the multiplexer was less receptive to noise, but also made analyzing data much easier.
All right, so we decided to design a new heatsink that was included more passive cooling techniques and was optimized. So our new heatsink has 2 sections, the bottom section and the top section, which is attached to the fins. These 2 sections are vacuum sealed together. And in the bottom, there's a chamber where we insert R134A refrigerant. We attach this panel to we attach this heatsink to the panel, and when the panel got hot, the R134A refrigerant in that bottom section started to evaporate. It would then move up each fin individually, consistently releasing heat as it did so, and when it reached the top of each pin would be cool enough so that the refrigerant would condense and drop right back down due to gravity. This process would continue to repeat, effectively releasing heat into the environment without adding any additional energy, because gravity was at play.
And one important factor in this heatsink, not only did it have thermosiphons embedded, but the entire profile of it was much, much smaller than the previous heatsink. So whereas the previous one would be very, very tall and impractical in most use cases, this one could be applied to a lot of different metals.
So, for our very first measurement, we did no cooling at all. We simply took the LED panel without any fans or passive cooling systems and took temperature measurements until it plateaued. As you can see, the temperature rose extremely sharply, plateauing at almost 120 degrees Celsius. So then we decided to make our system more complex by adding a variety of cooling systems and seeing which one worked most effectively. As you can see, the no cooling curve goes extremely high. With cooling fans, this was significantly lower, plateauing at around 35 to 36 degrees Celsius. And eventually, when we added our heatsink and our thermosiphon system, it almost matched the cooling fan system, plateauing just slightly above the cooling fans. This was a great accomplishment.
So we decided to explore our heatsink with thermosiphons a lot more, as it was our most effective system, other than obviously using the fans. And to analyze the data on this and to see if the thermosiphons were working and analyze the data, we took our 16 thermocouples and attached them to 8 different pins, one at the top and one at the bottom for each pins, as you can see the diagram on the left. And as before, we started data collection 2 minutes after and kept running it until the temperature was stable. And while doing this, we can see that very consistently, while the top temperatures were always slightly lower than the bottom, because of the thermosiphon mechanism, their temperatures were very close, even at equilibrium.
So this is just another graph of the comparisons of temperatures between the bottom and the top of the pin. And as you can see here, the bottom of the pin tends to be a smidge higher than the top, often varying by around 2 to 4 degrees Celsius. And this was taken at thermal equilibrium.
So, what do our results mean? So in all the cases, the bottom temperature at the evaporator was slightly higher than the condenser. However, after about 2 hours, both of these approached equilibrium, and this equilibrium temperature was well within the operating range of the pan. However, we want to ensure that this isn't just normal conduction and that our thermosiphons are working. Therefore, we did theoretical calculations on just a solid aluminum fin, and also we did a simulation, which we will talk about later. For the second set of our trials, we found that ambient temperature was actually a major variable in this, and depending on how hot it was in the day, we would get very different results. Because of this, we had to redo our experiments all on the same day to ensure that our readings weren't just a fluke, and they would work under varying operating conditions. So, first of all, for the simulation. Using SolidWorks, we 3D modeled our entire heatsink. As you can see, we have the top section here, the bottom section, and in here, the section where the refrigerant would be. And again, here's just another view of it. As you can see in the top section, you can see the holes where the refrigerant would go up and conduct thermosiphon, the thermosiphon would act. And then we put this entire model into ANSYS. And so once we put this, we selected the materials, and we analyzed the heat flow. We analyzed the heat flow through the material, and also the fluid flow of the R134A refrigerant. This part of our research was pretty problematic, as neither of us originally knew ANSYS, and we faced many hardware and software constraints, as well as time constraints. However, our final rough simulation ended up confirming similar results to this, but we were planning on redoing the simulation with not only more accurate materials, as the fluid inside in our simulation wasn't actually R134A, it was just it. And also we want to make sure we get the exact dimensions right for the actual heatsink. And we're going going to redo this simulation to confirm our results. On top of this, we did the calculations on a theoretical solid aluminum fin to make sure our thermosiphons are actually working. So with the cross-sectional area of the fin being given a fin efficiency of 90.7%, we're able to calculate a theoretical delta T at equilibrium of 16.02 degrees Celsius. Now, this is obviously very different from the 1.73 degree average we had after 2 hours. But therefore, we can conclude that it is not just conduction going on in our heatsink. The thermosiphons are in fact actually functioning. So, what can we conclude? First of all, we experimented these 3 passive cooling systems to cool down this high power LED panel, and we found that out of all of these, the most effective one was the heatsink with the thermosiphons embedded in between. While the first 2 systems, which were the original heatsink with the thermosiphons on the outside, and this heatsink with thermosiphons inside, provided excellent results, we do still need to continue doing research on it with the simulations, just to recreate our data and ensure that everything is working as planned. We would like to acknowledge Professor Zai in the back for helping us with the research, as well as Venkat Bilur. And we would like to thank the SGSU Department of Mechanical Engineering for letting us use their lab, and Intel Science Institute for training us.
All right, thank you. Questions?
Why that particular refrigerant? Is that just like standard use?
Yeah, it's just a pretty common refrigerant, and it's pretty cheaply available.
Well, yeah, go ahead.
On your first results page, you had multiple curves rather than just the fact. Yeah, what are the other curves? Like the
So,
green one?
yes, this yellow one is the temperature on the face of the LED panel without any heatsink, any fans, no nothing. This orange one right here is with the fans, so the one that cuts off right here. Then this green one is the heatsink, so it's this one with the heat pipes on it. So it's the, there we go. So the green one is that heatsink with heat pipes. This purple one is just that heatsink with no heat pipes or thermosiphons attached. And which one did I miss? Oh, and then this blue one is that heatsink with thermosiphons. Actually, you can, it's a little bit blurry, but at the bottom you can kind of see the thickness.
Okay. Other questions? Okay.
So you mentioned that the LED panel was for going was for space agriculture, and so you also mentioned that the refrigerant would fall back down because of gravity. How would that work in space?
So obviously, in space it would be a little bit less efficient, but okay. Well, first of all, it's not just for space agriculture. It's just any use for high power LED panels. So agriculture ground, just lighting up outdoor space, anything. And while in space, the gravity would not obviously be pulling it down. Still, just due to convection, the thermosiphon would still be working. Just due to the difference in the pressure of the hot.
Another question?
So I know you used gravity-based systems for the thermosiphons, right? Could you also use hydraulic systems, perhaps? Would that serve any benefit as opposed to the gravity-based systems?
Can you elaborate on like what type of?
By hydraulic, I mean basically instead of relying on gravity to circulate it, or rather you mentioned convection in general use cases, if there was some sort of pressure differential that could be created that could.
Yeah. So there is a slight pressure differential, so that's why even in space, the thermosiphons would still work just because of the temperature differential. So there is a pressure differential that would cause this to work even
Yes.
without gravity.
And those types of systems are also another type of passive cooling as well.
So why limit yourself to just LED? I mean, power is a major thing, and cooling thermals are a major thing in the industry. Why just LED? I mean, I see that equilibrium with your heatsink and siphon is like what, 50 degrees difference, maybe more.
Well,
I mean, if it works out.
It with basically any heat source. For our experience, we're just using an LED. But basically anything that emits heat and needs to be cooled.
Yeah.
This would be.
And cooling without power, right? That's
Yeah.
major.
Okay, any other questions? All right, I think that will finish the session. Thank you very much. Thank you to all.